In the previous video, I ran through the latest mass estimates and showed that 3I Atlas appears to weigh around 260 billion kilograms. That's already enormous by everyday standards, but cosmically speaking, it's surprisingly small. And more importantly, it's about 100 times less massive than estimates made just a few months earlier. That kind of discrepancy is not trivial. You don't casually lose 2 orders of magnitude in mass without something fundamental changing in how you interpret the data. At first, this looked like a simple refinement problem. Early observations are noisy. Assumptions get corrected. Models improve. That's normal science. But the December 26th update suggests something else is happening. The size discrepancy isn't just about better measurements. It's about what kind of material this object is shedding and how. Normal comet dust versus what we're seeing here. To understand why this matters, we need to talk about comet dust. When a comet approaches the sun, it heats up. Ice on its surface doesn't melt. It sublimates, turning directly from solid into gas. That escaping gas drags along solid particles embedded in the ice. But comet dust is usually extremely small. Typical comet dust grains are about 1 micrometer across. To visualize that, a human hair is roughly 70 micrometers wide. That means normal comet dust is more than 50 times thinner than a single strand of hair. These tiny grains are perfect sunlight reflectors. Because there are so many of them, their combined surface area is enormous. That's why comet tails glow so brightly even though the comet itself is tiny. And because they're so light, solar radiation pressure pushes them away from the sun very efficiently. This is why comet tails almost always point away from the sun. That's the standard picture. 3I Atlas is not following it. Dust that is 1,000,000 times heavier, according to calculations published on December 26th, the particles in 3 Atlas's sunward structure are not micrometer scale dust at all. They're closer to 100 micrometers in radius. That doesn't sound like much until you remember that mass scales with volume, not width. A particle that's 100 times larger in radius is about 1,000,000 times more massive. These calculations were done independently by Avi Loeb at Harvard and David Jewett at UCLA. Different teams, different methods, same conclusion. 3I Atlas is ejecting particles that are orders of magnitude heavier than normal comet dust, and that single fact explains several things at once, while creating new problems we'll get to in a moment. Why the sunward tail is such a big deal for months now, observers have been reporting a structure extending toward the sun, not away from it. This sunward feature stretches roughly 400,000 kilometers, about the distance from Earth to the Moon. Now sunward anti-tails do exist, but most of the time they're optical illusions caused by viewing geometry. The dust is actually in the orbital plane, and we're just looking at it edge on. 3 Atlas doesn't fit that explanation. This structure has been observed over multiple months from different viewing angles by different observers and instruments. It's persistent. It's stable. And it doesn't vanish when geometry changes. That means this is not an illusion. It's a real, physical stream of material moving toward the sun. Physics puts us in a corner. Here's where the math becomes unavoidable. Avi Loeb calculated how far dust particles should be able to travel toward the sun before radiation pressure reverses their motion. For normal comet dust, a few thousand kilometers at most. But 3 Atlas's sunward structure extends over 400,000 kilometers, more than 100 times farther than physics allows for tiny particles. There's only one way out of this contradiction. The particles must be much larger and much heavier. Once you plug in particles around 100 micrometers, everything clicks. These grains have enough inertia that solar radiation pressure takes days or weeks to stop them. They can coast sunward for vast distances before slowing down. Physics doesn't allow any other explanation. The next problem: how do you launch these things? So now we've solved one mystery, but created another. How do you eject particles that heavy? David Jewett's team modeled the ejection speeds for different grain sizes. The results are striking. 1 micrometer grains, approximately 22 meters per second, around 50 miles per hour. 100 micrometer grains, approximately 2 meters per second. 2 meters per second is basically human walking speed. That's just barely enough to escape the weak gravity of a small nucleus. So 3I Atlas is somehow managing to 6,127. Launch extremely heavy particle 6,128. At extremely low speeds, 6,129. In a coherent, sustained, sunward structure. This is already unusual, but it connects directly to the size mystery. Why the object shrank from 5 kilometers to 1 kilometer earlier, estimates suggested 3 Atlas was at least 5 kilometers wide. The new December measurements place it closer to 1 kilometer. At first glance, it seems obvious that the giant dust particles would explain the discrepancy. But here's the catch. The 1 kilometer estimate comes from measuring carbon dioxide gas escaping at high speed. Dust size doesn't matter for that measurement. The 5 kilometer estimate, on the other hand, came from orbital behavior. Or rather, the lack of detectable non-gravitational acceleration early on. If you see no measurable push from escaping material, the object must be massive enough that the thrust doesn't noticeably move it. Here's the key insight. Early on, 3I Atlas was losing a lot of mass, but most of it was in slow-moving, heavy particles. The momentum transfer was small, so the acceleration was undetectable. Later, when gas loss increased near the sun, the acceleration finally became measurable. That means both size estimates can be correct, depending on what phase of activity you were observing. But Avi Loeb suggests there may be something even stranger going on. What if this isn't dust at all? Here's where things get genuinely unusual. Loeb proposes that the dust particles may not be rocky grains at all, but chunks of ice. This sounds wild until you look at the chemistry. The James Webb Space Telescope measured 3I Atlas's composition and found something astonishing. Approximately 87% carbon dioxide, approximately 4% water. That ratio is flipped compared to normal comets. Carbon dioxide ice sublimates at much lower temperatures than water ice. So as 3I Atlas approaches the sun, CO2 starts venting first. Those CO2 jets can be strong enough to rip chunks of water ice off the surface. Here's the crucial part. CO2, ice sublimates quickly. Water, ice sublimates slowly. So the CO2 gas escapes rapidly and gets blown away by solar radiation, forming the normal tail. But the water ice fragments, heavier and slower, continue moving sunward, creating the long anti-tail. Suddenly, multiple mysteries align. The huge particle size, the slow ejection speeds, the persistent sunward structure. The changing size estimates all explained by a carbon dioxide-dominated comet shedding ice fragments. This would be rare. possibly unprecedented, but it does not violate physics. Where this leaves us. So where are we now? We know that. 3 Atlas is ejecting particles 1,000,000 times heavier than typical comet dust. Those particles explain the 400,000 kilometer sunward structure. The object's mass estimates change because early mass loss produced little acceleration. The chemistry is extreme, with CO2 dominating over water. Ice fragments offer a plausible explanation tying everything together. Is this object artificial? There's no direct evidence that it is. Is it normal? Also, not really. 3. Atlas appears to be an extreme natural outlier, an ancient interstellar comet experiencing solar heating for the first time in billions of years, responding in ways we've never been able to observe before. And that's what makes it fascinating. It's not that the physics is broken, it's that the object sits at the edges of what our physics has previously encountered. And as it continues toward Jupiter, we're about to learn even more. If you made it to the end, drop a like, leave your thoughts in the comments, and I hope you have a peaceful and curious holiday season.